thanks to Andy. I don't know where Andy's gone now. Anyway, thanks to Andy. He's put a really nice background on this talk, and we're just going to get a little bit more specific about one particular catchment. But Andy has already given you a lot of the background as to why this work might be important and putting some empirical data into the kind of framework for this. So I've got like the speaker and the pointer in one hand, so I'm going to be going between the two. So possible impacts of climate change on salmonids. Andy's talking a little bit about them already. Migration timing, food sources, density, hatching, fecundity, longevity. There's a lot of different places in the salmon's life cycle that climate warming can impact. And what we were interested in looking at was how might freshwater growth, so life history trajectories, how might they be changing in the coming century? And as you know, we're already, 2017, we're already well in the grips of climate warming, so it's not a theoretical thing anymore, it's already happening. So where we are, for those of you who aren't familiar, we're on the very west coast of Ireland, right on the continental shelf on the North Atlantic, and that little yellow, there we go, the little yellow thing is the Burrishoole catchment. So it's quite a small catchment, 100 square kilometres, a couple of lakes, 7 or 8 lakes, and 45 kilometres of river. But there we go. And it's a very nice experimental catchment. If you were to design an experimental catchment, it would probably look something quite like this. There's a lake at the bottom, and then right at the end, we have our 2 sea entry traps here, one of which is on a man-made channel and one of which is on a natural channel. So we can count every salmon and trout that's moving up and down from sea into freshwater and back out again, and every eel that's also emigrating out of freshwater, because once they get to here, this is essentially the sea. So it's not very far, it's about 20 kilometres up to the top of the catchment. So that's what it looks like from the air. And you can see the office just here. So one of the channels is here, one of them is just off the shot here, and then up the lake, and then this is the main channel up into the top of the catchment. So this is essentially the route that salmon will go up to spawn and come out again as smolts. So those are the sea entry traps, which Ken has just said. One of them has been there since 58 and one of them has been there since 1970. So we've got a total index of fish moving in and out of the catchment. That's not what I'm going to talk about today. Sorry. What I'm going to talk about is a small little river up the top of the catchment called the Shriva River. And it looks like this. This is kind of looking south down the catchment. And just here you can see it's another trap, which Phil is in the audience here at the back. He's my co-author. And Phil was instrumental in putting this trap in the early 90s as a way of impounding an experimental stretch of river so that you could plant experimental populations in a wild environment and not allow any integration with the wild population. So a lot of the data from this that I'm going to talk to you about today is extra data that we collected all the way along the operation of this trap. So it's kind of a fortuitous use of extra data. So when things come out of, it's also called the Rough River, when things come out of the Rough River here, like smolts, they go down here, they go down the downstream channel, and then out to sea if we're letting them out. Or they come back up here. But they can also be just totally killed as they're coming down the channel, so they don't get into the wild population. So that's what the trap looks like. So it's quite a small facility, but it's pretty effective. So the smolts coming down, or any kind of fish coming down, will be caught and measured in the trap. Little samples taken, whatever needs to be done on them. So it's like a little wild lab up the mountains. So that trap has been in operation at various times since the early 90s. It contains about 7,000 metres squared of habitat, so a couple of kilometres length of river, 1 or 2 metres wide. And it's been used for 6 common garden experiments assessing fitness of various populations of salmon and trout through the years. And many of those have been published, and they were mainly to do with genetic effects, integration, the effects of farm fish, survival of farm fish, some immunogenetic work. So these are extra data. There's a new project just about to start, which Phil can tell you about at dinner if he wants to, about some more work. So the work is ongoing, but this data that we're going to present here, there's about 14,000 salmon of wild and experimental origin have been passed through the downstream trap between 92 and 2012. Sorry, just spotted a typo there as I'm talking. So they're moving between 92 and 2012, similar numbers of trout. So that's all the fish that have been measured over the years. There we go. So if we look at the sizes of those fish, so these are the cohorts, 92, 93. Like, it hasn't been operating every single year, but a lot of years. So these are fish that would have been planted out as eggs and then come down through the trap over the next year, 2, 3 years. So the vast majority of fish moving out of the Burrishoole system are 2+ smolts. So 95% 2+ and 5% 1+. And you'll remember from Andy's graph in the ESC, I think there was 1+, 2+, 3+, 4+ smolts. The vast majority of Burrishoole are 2+ smolts. And some years we have the width of this bar here indicates the number of fish. So the wider bars are when there was a lot of fish coming down. So 93, 98, 2002 and 2009. So what we're interested in seeing is what is the kind of normal growth of a fish in a wild environment in the west of Ireland. You can obviously do this a number of ways, and I think a lot of people are going to talk about some tagging experiments as the day goes on. This was a kind of opportunity to say, well, we have all these fish data, thousands of fish lengths. Let's have a look and see what pattern we can see. So if we fit a seasonal von Bertalanffy model to all the fish, so each of those little grey dots is a fish as it comes down to the trap, and they're moving as 0+, as 1+, as smolt, so it's kind of big conglomeration of a load of fish. And you can fit a seasonal von Bertalanffy to that. Oops, sorry. So this is like a kind of theoretical march in the first year, march in the second year, march in the third year, and you can see there's a fairly seasonal pattern of steep summer growth, so they're really growing in the summer, maximum growth in the 8th of June, and then in the winter, in December, there's effectively no growth, which is this T0, there we go, is the winter, no winter growth function. TS is the maximum summer growth function. So between kind of September and December, growth pretty much flattens off, then picks up again as they're 1+, then flattens off again, and then out again as smolts. So if we look at the kind of sizes of fish that are coming out of Burrishoole, so in March of the first year, just when we first start seeing them in the river, they're about 3 centimetres. When they get to that mid-summer, when we're kind of electrofishing, the 0+ would be about 6 centimetres. These are salmon, not trout. At 1+, then the next summer they would be about 10 centimetres after they've had an overwintering with no growth, and then they're pretty much going out as 2+ smolts, somewhere up to 13 centimetres. So they're pretty small smolts, I think, relative to what you might find in some of the more productive rivers, somewhere between 11 and 13 centimetres. And that pretty much fits for all the cohorts there that I described. So this is just them all put together, but that pretty much fits for, and it also fits to what we see in the bigger traps at the bottom of the catchment for the sizes of smolts. They're about 11 to 13 centimetres. So the seasonal von Bertalanffy, it's very descriptive. It's a bit of a maths, issue, but it's very descriptive. But it's not much use for future climate projections because it's based on day of the year or month of the year. So date will stay the same, but as our climate warms, the amount of warmth that those fish experience in the river is going to increase, but date will stay the same. So if we convert the x-axis from date to growing degree day, which some of you will be familiar with, it looks more like this. So you can see here, instead of December in the first year, we have something like 3,000 growing degree days, and it's a nice straight line, so it's much easier to conceptualize. So the growing degree day, anybody operating in a hatchery will know that you need a certain number of growing degree days for a fish to hatch, and the same applies as you go up through the life cycle of the salmon. It's widely used in agriculture and entomology, but so far it's fairly limited in fisheries biology, but it's essentially applicable to anything that's an ectotherm, that's cold-blooded, living in water. I'm not going to go into this, it's just to say to calculate, for those of you who have never had to calculate it, the growing degree day, if you look at the average temperature of the water and you just add that up, so 5 plus 7 is 12, plus 1 is 13, plus 10, you get to 33. But you do have to take into account a certain temperature below which there's probably no growth happening, and that's like the winter, when you see that winter flattening off period, all they're doing is maintaining their body weight if they can. So we think in Burrishoole is somewhere between 3, 4, 5 degrees, so you subtract that from each of the temperatures and then you add it up, that gives you your growing degree day. So if you look at it in terms of growing degree day instead of date, we're looking at, these 0+ fish hatching when they're 3 centimetres, about 550 growing degree days, 0+ at 2,300, 1+ 4,600, and then going to smolt at 6,400 growing degree days. And I suppose what we were really thinking was, when in the year are they likely to experience those growing degree days at the end of the century versus now? How quickly will they accumulate those growing degree days in the coming decades? So this is like a fairly standard, for Ireland anyway, or for where we are in Ireland. The smolt run would be kind of the first 2 weeks of April. 0+ and 1+, they'd be 6 centimetres in September, 11 centimetres in 30th September, but then smolting around April of year 2, so 2+ smolts, and they're the equivalent growing degree days. So in future climate scenarios, when is that going to be in the year? So we have, as Ken mentioned, we're very lucky. We had some downscaled climate scenarios for the Burrishoole worked on by some colleagues from Maynooth. All I want to show you here is this black line is the water temperature the air temperature in Lough Furnace, where our met station is. And these are all the kind of climate projections that were downscaled to Burrishoole up to 2099, so the end of the century. And these are all the various kind of model scenarios, emissions, whether, there's a lot of carbon dioxide going into the atmosphere, not very much carbon dioxide going into the atmosphere. But you can see for Furnace, it's warming, or the observed data is increasing much faster than all the projections. So we're kind of well on that trajectory already. The thing with water temperature is that it's really rare. It's really rare to have water temperature data. But lots of places have long-term air temperature. So you can convert from air temperature to water temperature using using an exponential smoothing function. You can make a model of water temperature from air temperature. So that's what we did. Sorry, I'm not standing in front of it. There we go. So I'm just taking a couple of these emission scenarios to show you what the data looks like, and using the A2 emission scenario, which is kind of an elevated carbon dioxide thing. Now, for any climate scientists in the audience, I'm well aware that these scenarios, these A2, B1 emission scenarios, they've now been superseded by the newer representative concentration pathways published in 2014. So we need to update this data, a little bit out of date now. Having said that, the A2 scenario is very similar to what the IPCC is saying is going to happen, RCP 6 and 8.5. So this is just, if the Paris Agreement doesn't really kick in, carbon dioxide keeps increasing, the rate of climate warming keeps increasing, this is kind of what we're likely to see, which all indications are is this is what's going to happen, or probably going to happen. So if we look at what those temperatures look like for the Burrishoole, and so this is month of the year across the bottom, and your growing degree day. So you remember I said at the moment smolts are experience about 6,500 growing degree days before they smolt, before they get to that critical threshold that Andy was telling us about. And we can see that happens just around here at the end of April, May in the second year. The green lines there are our control periods. That's 1961 from a climate projection point of view. That's kind of 1961 to 81, I think. The purple are what the models tell us is our current temperature, although that's 2000, so we're already 17 years out of date. And then the future is 2097. So you can see the massive jump then as you get towards, and because growing degree day is cumulative, it kind of accumulates over the 2 years. So it mightn't be so bad when they're eggs, 0 plus, 1 plus, but after 2 years, there's quite a big temperature differential after 2 years. So just to put it in perspective, this is actually the observed data in Burrishoole, and you can see it falls halfway between what the models tell us is our control or our current temperatures and well on the way to what the future scenarios are projecting. So we're already quite far along that curve. But again, if we go back to this table here, this is really what we're interested in. So our observed salmon growth, we said first sight is about May, 0 plus 6 centimetres will be about September of that year, 1 plus about September the second year, 11, and then smolting at 13 centimetres in April. If we run that with those future climate projections, those temperature projections in the future, so this would be for the period 2070 to 2099, the first sight doesn't change that much. Well, a little bit earlier, maybe April, March. They maybe would reach 6 centimetres about a month earlier. They would reach 11 centimetres maybe 2 or 3 months earlier. But the big difference is because of that winter lull in growth, the big difference is apparent at smolt age. So instead of getting to 6,400 growing degree days in April of year 2, they might now start experiencing all that by late October, November in year 1. So a full couple of months, 3 or 4 months before, they might reach that critical threshold that they could smolt if they wanted to, if they had all their physiological stuff in order. They could go to sea. Obviously, they're not going to go to sea in November, but they could theoretically. Okay, so there's kind of 2 ways this could go. And Andy gave us some, this is based on a really big assumption that the fish continue to spawn at approximately the same time of the year, which in our case is always Christmas week. I mean, it may be that, so this is part of a wider picture. Fish growth is just one part of the whole process. So the implications for future scenarios, either we're going to be starting to see really big 2 plus smolts, so they're just going to grow that extra bit bigger and we'll get ones that are 14, 16 centimetres, better marine survival, less predation, more eggs in the returning adults, or we're going to start seeing smaller 1 plus smolts. So they just will smolt maybe the year before, but they'll be a little bit smaller, maybe even 9 to 10 centimetres, although they haven't reached that threshold of 11 to 12 centimetres to smolt. And they would have poor marine survival, more predation, less eggs in the returning adults. So to put that in the context of wider smolt production models, which I think Alan's going to talk about and various other people are going to talk about. There's a nice paper from Richard Headwater and his colleagues about modelling the complete life cycle of salmon. It looks really complicated, but what I've just talked about there is essentially this bit here. So you've got river temperature affecting growth rate, and then that affects your par size, your smolting probability, your post-smolt abundance. And that then feeds into your adult abundance, sea returning adult. So you think it's one small part of it, but actually it's central to the whole thing. So the freshwater growth is central to the whole production of salmon smolts. Just a couple of extra slides about where we're headed with this. We do have a lot of trout data also to look at. Now, as many of you know, the sea trout population in Burrishoole is pretty much extinct, but we do have a large resident population, and we have a lot of data for that. So to just see, is it impacting trout and salmon in the same way? And then obviously pit tagging will give you that individual growth. So you tag a fish now, you catch in a couple of months, you measure it again and you get the individual growth. And that's maybe a more exact way of measuring this. But we already have some indications of what that's going to tell us. And then finally, I'm just going to put in a plug here, and Andy mentioned it about long-term monitoring. There's a nice paper that just came out recently showing that long-term studies, which are fairly frustrating to work on, fairly hard to get funding for, fairly hard to analyse the data, but they do disproportionately contribute to policy in a very big way. So government agencies and people determining policy for fisheries conservation rely heavily on long-term studies, much more so than short-term studies. this wasn't just about fish, it was about lots of different things, but you can put fish in here. So I guess just for everybody who is collecting these data, they're really important. And you can see from our stuff here, we were able to draw some nice conclusions based on data that we weren't really necessarily collecting for this purpose. So when you're collecting long-term data, there's lots, you probably use the same data set 20 times to do 20 different things, and that's really important. And to make that data publicly available as much as possible. Okay, and just to say at the end, obviously 14,000 fish to measure. There was a lot of people involved, as well as our co-authors, a lot of other people. Just say thank you to all of them. And you can contact me here or on Twitter if you have any questions. Thanks a lot.